pleasure for me to welcome Hal Varian here among us. And most of you know that he's a professor at UC Berkeley and a chief economist at Google. And one of the most famous things for what he did at Google was designing their ad auctions. So just out of curiosity, I Googled you and I searched for Varian on Google and to see what sponsored links come up. So in New Zealand, we got vacuum pump parts coming up every single time. And then I was refreshing the page, and occasionally also that got chromatin wrapping and wasn't always. And then I called my friends in the US and in Prague and asked them to do the same thing over there. So in the US, we got Hal Varian on Amazon, and in the Czech Republic, they actually got no sponsor links at all. Huh. So I'm looking forward to your talk and hope this is going to explain it.
Okay. Well, thank you very much for that nice introduction. One time, there is a company called Varian Associates that make all these electronic and mechanical devices. And one time when I gave a talk in Austria, one of the staff was put in charge of handling me. And I said, how did you get this great duty or honor? I'm not sure which it was. She says, well, I'm in charge of the Varian, you see. And so she had to handle the Varian computer. So they thought she was therefore suited to handle me.
Your name is Hal.
Yes, I know. Fits on both lines. So today I want to talk about the Nash equilibrium in the Google auction. And I do want to correct one slight thing in that introduction. The Google auction was in place before I got to Google. So I didn't really devise the auction. That was actually devised for some engineers. And I can tell you a little bit of the history there. But when I came, Eric Schmidt asked me to look at the auction, see if I could understand the economics of it. So I do think I was the first person to really create an economic model of the auction, and that's what I'm going to talk about here. So in fact, the history of the auction goes like this. It was developed, the idea of auctioning off search results. So that's search results, not ads, but search results was developed by some people in Pasadena at a company called the Idea Factory, I think. And legend has it, I haven't really been able to verify this, but the claim that I heard from the folks at Caltech was that one of the people at this company had taken a course from Charlie Plott in auctions. And at that time when search engines were becoming popular, he proposed that they construct a search engine by auctioning off the search results. Well, it turns out that didn't really work so well because users didn't particularly like that model, and then they split it in a way where they would auction off the ad space and then generate the search results algorithmically, and they formed a company called GoTo, and GoTo commercialized the ad auction part of this. And Google, in the fall of 2001, was looking around for a business model. They were already selling ads that appeared at the top of the search results, but the prices of those ads were set by the sales force. So if you were making a pitch to a dog food manufacturer, you would say, well, look here, you can buy up the words for all the dogs, and when people search for their dog, they'll see your ad for dog food. And the advertisers understood this model as a model where you paid per impression. So every time somebody saw your ad and saw your brand, then you had to pay Google for that. But how did you set the prices for the keywords? How would you determine those prices? And the sales force had a very difficult time doing it. So when people at Google saw the ad auction that was used by GoTo, by this point had been renamed to be Overture, they thought this was a good model for Google to follow. So they took that model of the search auction and they enhanced it in a couple ways. One way is they made it a second price auction, so the amount that you didn't have to pay your bid, you had to pay roughly speaking, the bid of the person below you. And then they added another enhancement, which is you didn't have to pay, you weren't bidding, the ads were not ranked by your bid for click, they were ranked essentially by your bid for impression, Okay, so I'm going to explain that. That's probably a little mysterious at this point, but I'm going to explain that in a few minutes. So in any event, that was put in place in February of 2002. I came to Google in May of 2002. The model had been performing pretty well, and AOL had just decided to take on Google as their monetization option. So they wanted to use Google to monetize the search pages. And but I have to say, at that time, nobody was quite sure what the economic foundations of the model looked like, and so my contribution was to develop the kind of the theory of the model. So in this case, it was really art imitating life, not life imitating art. So that's the little pitch, and let's see. So you think this will advance? Well, have to use a finger. All right. Well, that doesn't work either. Let's see. No, we'll go up here. Try this. There we go. Okay. So here are the simplified auction rules. So I'm going to work through this model, and then I'll throw in a little complexity, but we'll do the simple model first. You think of each of the advertisers has a value for a click. So you think about that as how much they're willing to pay for a visitor to their web page. So the easiest case might be that they're selling something, and then the idea is somebody clicks, they come to their web page, there's a probability that they buy whatever it is they're selling, and then at that point, the advertiser realizes some profit. So one model for that value per click would be the expected profit per visitor. Okay? So that would be the simplest model. There might be other considerations. Maybe, if you're buying a car, what happens is nowadays the automakers are very, very sophisticated. They attach different values to visitors depending on what you do in the site. So if you type in your zip codes or show me the local dealer, that's a really good sign you're interested in the car. And if you play around with the configuration tool and look at the colors and look at the different models, that's another really good sign. So you can kind of value the visitor to your website in a more sophisticated way. But the simplest case is just think of that as the expected profit that you make from the visitor to your site. So then in the auction, each advertiser announces a bid. So that's how much they're willing to pay per click in this case. The guy who bids the highest gets position 1, second highest gets position 2, and so on. And then the bidder in position I pays a price per click determined by the bid of the advertiser below. So the price that advertiser I pays is the bid of the guy in position I plus 1. So every economist says, oh, it's a victory auction. No. Turns out it's not a victory auction. In the case of just one item, it would be a victory auction. But it turns out when there are multiple items here, the truth-telling is not the dominant strategy equilibrium. And you'll see that in a few minutes. And in fact, the reasoning that went into this second price auction, what some people now call a generalized second price auction, is different but related to the economic argument. It's really an engineering shortcut. Because suppose you were in this auction, you had a first price auction. Well, what would you want to do? You'd want to cut your bid a little bit and pay a lower price. And how far would you want to cut your bid? Well, you'd want to cut it as far as you could and still retain the position that you have. So if you're in your position 2, you'd want to check in and see, well, if I cut my bid by a penny, would I still be in position 2? If I cut it by 2 cents, 3 cents, 4 cents, until you just kind of lost your position. So you'd want to pay the minimum price you could to get the position that you wanted. And that means you'd have to log into the system all the time. And that's going to put a big load in the system. So instead of doing that, they said, let's just lower the price to where you'd want to do anyway, and then they won't have to keep revising their bids all the time. So that was definitely an improvement over the way things had been before. Okay, so then the payout to bidder I is the value per click minus the price he has to pay, the bid of the guy below him, times the number of clicks he gets. So the click-through rate, or I think in this case it's just easy to think of the total number of clicks that the advertiser gets. And it turns out that when you look at the click-through rates, they vary in just the way you'd think they'd vary. The first position on the page gets the highest number of clicks, and then the second position, the third position. It's basically monotone. So what you want to do is you want to put the highest value bidders, in some sense, in the most prominent position, which means the place where they're most likely to get clicks. Now there's a little bit of abstraction. In real life, there's two ads at the top of the page, and there's the ads down the right-hand side of the page. The ads at the top of the page tend to be much more prominent. There's kind of a separate auction for those, but this is a pretty good first pass for how the auction works. And there's this one little parenthetical expression. The real auction, the actual auction, is going to order the advertiser by the ad quality. I think of that as kind of the expected click-through rate that ad would get times the bid. So it isn't just the bid, but it's bid per click, but it's the ad quality or the predicted click-through rate times the bid. And that adds some complications, but I'll describe that in a minute or two. Okay, so that's the model we want to look at. Simple, I refer to it as a position auction, and it's also known as a generalized second price auction. Yes?
Does the advertiser pay only if the user clicks through, or does he pay per impression?
No, he pays only if the user clicks through. So it's a pay per click model, and this was good because the advertisers only had to pay for the actual visitors because they didn't really know how much an impression was worth. And remember last night, 2 days ago, my talk indicated there is this kind of division of interest between the publisher who has space to sell, and he wants to sell that ad impression to the highest valued bidder. And the advertiser, well, he doesn't necessarily want to pay for the impression. He actually wants to pay for the click, or more generally, for the sale, for the actual. So he wants to pay only when something really pays off. And so what you want to do is align the interests of the advertiser and the publisher by allowing the publisher to sell impressions and the advertiser to buy clicks. That's kind of a cute trick, which we'll get to in a few minutes. Okay, so that's the auction rules. So forget about the impression business for a few minutes, and we'll figure out this model first. So here's an example. You've got position 1, 2, 3, 4, and let's just suppose there are only 3 actual positions and there are 4 bidders. So the click-through rate for the guy in position 4 is 0, which just means his ad doesn't get shown. So they've got values, V1, V2, V3, V4. There's a number of clicks that you get in position 1, 2, 3, and then 0 clicks in position 4. And then you've got the bids, and then you've got the profit. So now, when we analyze this from a game theoretic perspective, we have to say, well, what would happen if somebody changed their bid? So let's suppose a guy in position 3 wanted to move up to position 2, so then he would have to beat the bid of the guy in position 2 to occupy that higher position. So he'd have to bid B2 plus a little bid increment to break the tie. But if 2 wanted to move down to position 3, so guy in position 2 wants to move to position 3, then he only has to bid B4 plus epsilon. So if you want to move up, you have to beat the bid, but if you want to move down, you have to beat the price. There's a little asymmetry there. Okay, so let's see, I've puzzled over that for a while. We could say a set of bids is a Nash equilibrium if bidder I makes at least as much money, at least as much profit by being in position I as by being in any other position, under the usual assumption that nobody else changes their behavior. So this just says the left-hand side is how much money the guy in position I is making now. The right-hand side is how much he would make if he moved up to position J, so J less than I, when you move higher up the list. And the second inequality says how much he makes now has to be at least as good as he would make in any other position moving down. All right? So those are the inequalities that characterize a Nash equilibrium. Well, that's pretty easy. They're nice linear inequalities, right? So we can manipulate them here. rearrange them a little bit, what it says is, on the right-hand side is how much the guy in position I is paying for clicks. And it says that it's got to be less than the amount he would pay if he was in position J, plus the value of those incremental clicks. So it's like all of economics. Some marginal argument sneaks in there somewhere or another. And what it says is when you move up or move down, you want to look at the value of the clicks you get by moving up or the value of the clicks you lose by moving down. So any set of B's that satisfies those linear inequalities is an equilibrium. There's going to be an infinite number of solutions in general, except in very degenerate cases. So let's try to focus on ones that would be interesting. And two interesting ones would be the set of equilibria that gave you the maximum revenue and the set of equilibrium that gave you the minimum revenue. Okay? Well, those are linear inequalities, and the revenue is linear, so there's just two different linear programming problems. You could maximize your revenue subject to the equilibrium constraints, or you could minimize your revenue subject to the equilibrium constraints. So you can play around with doing that. It's very easy to solve that problem. But it's not very satisfying because you haven't really characterized the equilibrium in any way. So one of the things you can do is you can find a subset of those equilibria where you can solve out explicitly for what the equilibrium looks like. So that's what I call a symmetric Nash equilibrium. And it says the following. Suppose you can find a set of bids that are monotone. So bid 1 is bigger than bid 2, bigger than bid 3, and so on. And that satisfy the inequalities that are written in the second line there. Okay? So those are the inequalities that says, those are the same inequalities we saw on the previous slide, but it's just for moving up, I guess. All right? But now we're going to say let's satisfy them for all I and j. So then we must also satisfy those earlier Nash equilibria that I showed you there. Just write down that inequality. This inequality uses the monotonicity, and this inequality is what I have written up there. And now you see you satisfy all the inequalities I had before. So that shows you that if you satisfy those symmetric Nash equilibria inequalities, you'll satisfy the inequalities earlier. So this is a subset of the previous set of all equilibria. Okay? And the nice thing is, it turns out with these inequalities, they're very simple and easily manipulated. Okay? Now, why is that? Well, I said you have those inequalities for all j, so I want to consider moving to any position. But it turns out if you write down those inequalities for moving up one step or moving down one step, you automatically satisfy the inequalities for moving up any number of steps or moving down any number of steps. So that's the first nice thing that happens. If you satisfy the one-step inequalities, then you satisfy them all. And that's, you could just write down the inequalities and look at them in a minute. And then you get a very nice recursion to solve for a Nash equilibrium. So you get this recursion here on moving up a step, one step, or recursion for moving down one step. You get a relationship between the bid, the amount that you're paying per click and the position you're at, and how much you'd have to pay to move up one or down one. And then you can just turn the crank and crank out the entire equilibrium. So the largest and smallest bids that solve these symmetric Nash equilibria, in fact, are determined by those inequalities. Okay? So it's very simple and clean solution. Turns out that's the same thing as a paper that's written simultaneously or independently with this by Edelman, Ostrowski, and Schwartz about internet advertising, the generalized second price auction. So they had 1/2 of those inequalities. Okay, now, so let's try to interpret those a minute. Let's just take the lower bound. So the lower bound looks like that. It says the payment that the guy in position I-1 is making is equal to the payment that the guy in position I is making, plus the value of those incremental clicks. You divide through by the clicks, and then you see right away that the bid of the guy in position I is going to have to be equal in equilibrium to the bid of the guy in the position below him. Convex combination of the bid of the guy in the position below him and the value of the guy in position I. So right away you see it's not a truthful equilibrium. You aren't just reporting your value. You're reporting a weighted average of your value and the bid of the guy below you, where the weights depend on the relative click-through rates. So the first excluded bidder, so here's a guy who doesn't show. Well, there's a little bit of ambiguity there, but let's just assume he bids his true value. You can make an argument for why it would be in his interest to do it, because he might appear, throw a little noise into the situation, he might appear. And if there's not an excluded bidder, then there's a reserve price in the auction. So there's a minimum price you have to pay to appear. And you can solve this recursion by repeated substitution to get an explicit solution. Yes?
So you may have mentioned this earlier, but when these guys bid, do they know, and when the actual Google bid, do they know what the other bids are?
Yeah, so that's an excellent question, and the answer is no, they don't know that explicitly. Of course, it's easy for them to experiment, so they can tweak their bid up or down, and they get a report. Basically, if you're bidding on something that's very popular, there'll be lots and lots of queries and lots of ad clicks, and you can experiment with different positions, but you can't. You aren't shown that information.
When you do your modeling, are you assuming it's known?
Right, I assume it's known in the sense that I assume that they're exploring, as in the usual kind of Nash argument, they're exploring the possibilities, and they're kind of figuring out how much they have to bid to retain a particular position.
So I don't know in game theory, but when everybody else is also exploring at the same time, can you end up getting away from it?
Yeah, so the question is, if we try to write this down dynamically and look at the sort of everybody exploring at the same time, could you get strange dynamic behavior? And we played around with that a little bit. You can get some strange behavior. But I will actually address that, a kind of refinement of that question in a few minutes. Because the other thing that's a little bit unrealistic about this model is that you don't get to bid on an auction-by-auction basis. You set a bid, and that's going to apply until you change it. So you might be potentially competing with different advertisers. So actually, you'd like to elaborate this model, and I'll give you a more general version of it, where you're kind of smoothing over a bunch of auctions, not just doing it on an auction-by-auction basis. Okay, so anyway, you can solve this recursion, and you get the bid of the guy in position I. That's written there on the page, and you see what it is you just look at the values of everybody below the guy in position I. There's their value, and you look at the value, the incremental clicks of moving from position I, or position J, to position J minus 1. So that turns out to be what the guy in position I should be bidding. And the total revenue you get from the auction is given by this expression. Okay? So now I started out on the previous slide saying, I started out at the top of this slide saying, well, let's take the lower bound, and we solve out for that. We can also solve out doing exactly the same things for the upper bound, and I think that's on the next slide. Yeah. Wait, did I go to? Let me just back up a second. No, there. Okay. So you can do exactly the same thing to get the lower bound, so now we get a nice explicit solution between the upper bound and the lower bound. And on the next page, I want to say, well, that was fun, starting with values and going to bids. So we said if we knew the values, this is what the equilibrium bid should be like. We also go the other direction, right? You could also say, here are the bids. What do the values look like? So a symmetric Nash equilibrium satisfies those inequalities I wrote up at the top of the page. It says you doesn't want to move up, you don't want to move down. If you rearrange that, it says your value is then trapped between a lower bound and an upper bound in equilibrium. And what are those upper bounds and lower bounds? Well, if you look at it a minute, it turns out those are just marginal costs. Because this is the cost, this is a guy in position I, he pays the price, which is equal to the bid of the guy below him. So this is how much the guy in position I is changing. This is how much the guy in position I is paying. This is how much the guy in position I plus 1 is paying. This is how many extra clicks you get by virtue of being in position I rather than position I plus 1. So it says your value has to be at least as big as the incremental cost per click, right here. And why is that? Because if it wasn't, you wouldn't want to buy those last clicks, right? I have to be willing to pay for those clicks that I'm getting. I want to bid up as long as my value exceeds the incremental cost per click. I want to keep moving up, and then as soon as the incremental cost per click exceeds my value, I want to stop. So you get a nice simple bidding rule. Move up as long as the incremental cost per click is less than my value per click. And then when I get to a position I like, it says the value of my clicks is not, it's not worth it for me to bid anymore because I don't value those incremental clicks enough to warrant increasing my bid.
Are the players in this game sophisticated enough to know the X's?
To know the X's. Yeah, they figure out the X's pretty well. But again, you see, you don't really have to calculate the equilibrium. You can just try it out and see. This is a repeated game is repeated billions of times. Any one advertiser, it's not billions of times, but any one advertiser is produced, it's repeated many, many times, and the advertiser can just say, well, I'll bid a little more and see what happens. Well, see how many extra clicks I get. Did the extra amount I have to pay the extra clicks I get compensate me for the extra amount I had to pay. So they don't really have to be hugely sophisticated in figuring this out.
But there's lots of things happening. I mean, you got, different days of the week, different months of the year.
Well, it's true. It's true, but what happens is advertisers, first of all, they do this all the time. They're exploring to figure out what the optimal bid is for them. And they're fairly aware that if they wanted to bid more, they could bid more and get more clicks. And so the question is, just they want to compare the value of those clicks to the cost of the clicks.
So Google has a chief economist and Yahoo has a chief
Right.
economist. Other people don't.
Right. How do they figure it out? How can they survive without a chief economist? It's amazing. Well, what happens is there is, of course, intermediary. There's something called SEMs, or search engine management companies, or SEOs, search engine optimization. So what you do is if you're very interested in optimizing this, you'll hire people, intermediaries, who specialize in doing the bid setting and all this stuff. So it's just like any other form of advertising. There's the publisher, like TV, there's the advertiser, and then there's the ad agency that's an intermediary. So in the search engine advertising, there's an intermediary who kind of understands the advertiser's objectives, understands the bidding model, and then tries to optimize for you. Yes?
How often can someone change his or her?
As fast as, in fact, faster than they can type, because you have an API, so that allows the computer to be changing the bid continuously. So it's just a mechanical, whatever. Now it gets updated, it has to propagate through the system and things like that, but basically you can change your bid continuously.
So it's like airline pricing now.
Yes, right. So you can change your bid on at will. And of course, the other thing that people, when I talk about an auction, of course, every time there's a search on Google, there's an auction. All right? So the auctions are occurring also in real time. Yeah.
So what defines the market here? As who are you competing against? Is it specified by country boundaries?
What defines the market? Uh-oh. That's a trick question, I can tell. No, what defines who you're competing against? Well, so what happens is there's a whole other set of rules about who's in the auction. And for example, the advertiser, when they do their keywords, so they're picking keywords, and there is this somewhat subtle distinction. The query is what the user enters. The keywords is what the advertiser enters. And the question is, does the keyword match the query? So if I have, I mentioned this again a couple of days ago, I could have the keyword diamond, or I could have the keyword diamonds. And if I specify I only care about exact match, then diamond and diamonds would be different. If I said, oh, but it could be broad match, so then in that case, diamond and diamonds would be considered the same. So you could have, you'd probably want your people to match diamond queries, or do you want it to match engagement rings, right? Or do you want it to match jewelry? So that would be a very broad interpretation. So the advertisers get to choose whether they want broad match, exact match, negative keywords. So I said I want it to match diamonds, but not baseball diamonds. Or you can have phrase match, where I want it to match a certain phrase, etc. So there are all these different choices you have about how close you want the keyword to be in the query, and that's going to determine the number of potential competitors in the auction. Yeah. Oh, and by the way, just to your other question about geography, you can also specify the language and the geography, of course. You can say, I want this only to apply to bids in New Zealand, or only to apply to bids in this 50-mile radius of Christchurch.
Well, the answer is that the advertiser actually defines the market.
Right. The advertiser defines the target audience that he wants to reach. Yes?
And just following up on that, also restricted by time of day, so I'm only interested in searches done in between these hours every day.
Yeah, so that's known in the industry, that's called day parting, and you can also specify bids in day parts, although you can also use the API to change the bids according to your own rules. So you can get a finer degree of graduation than you might otherwise. Okay, so let's look at the next slide here. So that's just what I said before. If you think about it, those inequalities say that in equilibrium, the incremental cost per click must be increasing with the click-through rate. Why is that? Because suppose the incremental cost per click went down at some point. Suppose it declined as you increase your bid. Okay, well, what would that say? That would say you bought expensive clicks and then passed up cheap clicks. The incremental cost. So that couldn't happen in equilibrium. So if you think about it, what you've got is it slopes upward for the same reason a supply curve slopes upward. It's really the second order condition I've got here. So you can think about having a supply curve of clicks, and as you increase your value per click, then you can look over here and see how many clicks you should get. So the other bids in the auction are basically defining a supply curve as you contemplate where you'd like to be. So there's other bidders that are determining the price points, and then you get to pick your position subject to the rules of the auction. Basically, it's tracing out this kind of supply curve of clicks. Now, one thing you can do, just to drive this point home a little bit, is you can plot the clicks on the horizontal axis, and you can plot the expenditure on the vertical axis, and then the incremental cost per click is just the slope of those lines. That's the incremental cost per click. And if you have your profit is going to be a straight line, the ISO profit line, and it turns out this is the negative of your profit, the vertical intercept here. And so what you want to do is you want to find the most profit maximizing, most profitable point on this set of positions. You're just trying to find the point where you're, see if I can get this to work. You're trying to find the point, let's see. No, it's not going to work. Well, some days that animates. Yeah, some days it animates. But you could just imagine it. You know, you have good imaginations. Think of this line as just moving down here and finding the profit maximizing point. And if the line were flatter, if you had a lower value, you'd move down and find this is the most profitable point. And if you had a higher value, you'd find that up in the top was the most profitable point. So it's just a simple kind of convex optimization problem. And, oh, this is the one that animates. There we go. Let's see if we can get this to work. No, still not working.
Is the top left up there, the little icons at the top? No, it's
No.
of the square. The square that you've got.
No, they're not doing it. Anyway, so this is maximizing profit means shifting the ISO profit line as far down as possible. You can just imagine it moving. And the same thing if you think about what would be the range of values which would be consistent with this is the profit maximizing point. It would just be you could rotate this line till it was this steep, or you could rotate it was this flat. Those are just those upper and lower bounds that I had before. So if you're observing that this guy is optimized at this point, then he couldn't have a value that's any greater than that, and he couldn't have a value that's any flatter than that, simply from the geometry of the figure. So it's a very, very simple model in this respect. Now, so I told you that life was a little more complicated than that, so let me throw in the additional complication now. So what happens is you don't just want to have people bid on a per-click basis. And let me explain why. Suppose that we're thinking about bidding on jet airplane, okay? So we have two bidders. There's Joe's Jets and there's Moe's Models. And so Joe's Jets, he sells jet planes. So he's willing to pay a lot per click, right? A lot per click. But there aren't that many people who want to buy jet planes, so he might not get very many clicks. Moe's Models, he sells model planes for a few dollars. But there might be a lot of people that want model planes. So he might get a lot of clicks. So what you want to do is you don't want to show the ad that has the highest value per click. You want to show the ad that has the highest expected revenue, which is going to be the value of the ad times the number of clicks that you get. Okay? So it could well be that the guy who has the lower value per click actually sells a lot more product and gets a lot more clicks, and so you end up, it's more profitable to show that guy in the top position. So what you do is you think of the actual click-through rate, call that ZI, is the product of a position-specific effect. Okay, that's how many clicks you get just by virtue of being in a more prominent position, and an ad quality effect. So call that effect EI. And that's sort of how many clicks you get from this ad in an average position, something like that. So it's a multiplicatively separable model. You've got the click-through rate ZI. You've got the actual number of clicks you observe is a position effect times the quality effect. And so when you change positions, if you have an ad that attracts a lot of clicks, then you kind of take that quality along with you. So Moe's Models will still get more clicks than Joe's Jets, whatever position it appears in. And so you have to adjust for that. So you order the bidders now by the EI times BI, the ad quality times the bid. And if you want, you can just think of that ad quality as being the predicted click-through rate. So the ad quality is talking about clicks per impression times the cost per click. That's a cost per impression, or a price per impression. And now this comes back to what I was saying earlier. The publisher wants to sell the position, or Google in this case wants to sell the position to the advertiser who's going to give it the most revenue. Okay? So the way you want to do that is you want to say, well, what's the value per impression? Who has the highest value per impression? That's who I'm going to sell it to. So you want to look at their cost per click times their clicks per impression. And so you have to estimate the expected number of clicks per ad impression that a particular ad is going to get. And that turns out to be the world's biggest logistic regression, because there are millions and millions of advertisers, and what you're trying to do for each one, you take all the ads and you try to estimate from the past history and from characteristics of the query and the keyword and the ad, you try to estimate how many clicks this ad will get.
So what are the arguments in logistics regression?
So the biggest argument is previous history. So when you had this ad and this query, what was the number of clicks that you got? Okay, historically. But then we adjust for all those kind of things you were talking about. Things like day of week and country and language and the ad creative and what ads like this, so you can have a similarity. So what ads like this kind of click-through rate they experienced and so on. So you can have actually millions and millions of observations and thousands of predictors, or some cases millions of predictors if you count that constant term, and you can then try to predict what the click-through rate will be. But generally it's tied down to the historical evidence. It's tied to the historical record.
So when you're selling ads in Clinton and Obama a year before the election, you wouldn't have done so well.
Yeah, so what happens is when an ad just starts out, the predictor is based on sort of gross observed characteristics of that ad. And then as you gain more and more experience, it's based more and more on how that ad has actually performed.
Like I was just thinking in the bidding markets a year before the election,
Right.
Obama didn't even register on the list.
Right. So what would happen then is if you had ads that were bidding the same amount, and one was more likely to get clicks than others because the brand name was better known, like Clinton versus Obama, then you would see that ad ranking ahead because it would be more likely to get the clicks at a given bid. But then as the brand name evolved, then you might see it change.
So you're going to stay working on that?
We've looked at this election stuff. It's very, very interesting to look at the election behavior. Anyway, so what happens? So we want to add this to the model. So now what happens is the price you pay is going to be just enough to retain your position. So now we write down this inequality, and that says the price you pay is going to be your bid divided by the relative ad quality or the relative predicted click-through rate. Okay, simplest case. Okay, and then the Nash equilibrium, I take exactly what I had before and just substitute in that new expression for the price, and I get the symmetric versions of the inequalities just as I had before. So it's really not too much different. I've just added this E term, and I can go through the same operations and get out same sort of expression as I had before. So this is just as before, but now it's a bound on the value or the implied value per impression of that advertiser rather than the value per click. Of course, if I divide by the predicted click-through rate, then I get back a bound on the value per click, just as before. So works both directions. If you've got a Nash equilibrium, then you get this bound. And if the intervals are non-empty, then you can always find a set of values that satisfy those inequalities that are consistent with observed bids. So a necessary and sufficient test for Nash equilibrium is to see whether the incremental cost per click is increasing in the click-through rate. Okay? So we can go look. And here's some pictures. So on the bottom axis is the click-through rate for being in the different positions. On the vertical axis is the expenditure or the cost for being in those positions. And the first example up there is for debt consolidation. And the second example is for dial-up internet provider. And the black line is the actual distribution of the cost function. And that's what it is. Down below you have a quantity, how many clicks you get. And the vertical axis is the cost of those clicks. And the theory says that should be an increasing convex function. And in practice, it's an increasing almost convex function, right? So the black line is the actual, and the red line is the closest monotone convex function to that line in terms of sum of squared residuals. So you can say, given a set of data, find the smallest perturbation of that data that fits the model, namely you have an increasing convex function, and then you ask, was that very big? Did you have to perturb the data very much? So this is what's known as connect the dots econometrics. We just connect the dots. We connect them in a way that makes sure that we have an increasing convex function. There's a couple more. That's fantasy football. Here's one for New York City business. And of course, there are many, many thousands, indeed millions of these. So you can plot them all out. Here's a little example. I looked at about 2,500 randomly chosen keyword auctions and asked what's the average absolute deviation necessary to satisfy those inequalities, and the answer is I had to perturb the data about 5%. Median 4.8%, mean about 5.8%, and here's what the histogram of perturbations look like. So in some cases you had to make a fairly large perturbation, but in most cases on average the perturbation was really quite small. So remember, this is how much you have to preserve the observed relationship between clicks and cost in order to satisfy the necessary and sufficient condition for a Nash equilibrium, namely that the cost function is monotone and convex. Yes?
Where do you think we're looking at those, the outliers, the ones where you have
They were usually just like a couple points, like a very, I mean, I guess it takes 3 points, because 2 points is a straight line, that's okay. But when there's 3 points and one is way off. So I think it comes down to what you were saying earlier, namely that there's a learning process. You wouldn't expect to fit the data perfectly and continuously because people are discovering, well, I don't have the right data. I'd rather be higher, I'd rather be lower. And sometimes you're just getting somebody who's kind of caught in the middle. Okay.
But you should be able to test for that, shouldn't you?
Whether they changed, yeah, sure.
You were saying you can track these guys where they're, there's some advertiser out there.
Yeah, so you could see that if they...
experimentation going on,
right.
Then the fit is better or worse.
Right, although I'll tell you the way I actually did it, which is kind of more convincing, except I can't show you the numbers. What I did is I went through and I calculated the implied value per click. So here, for this is one auction, and I've got the raw lower bound on the value of a click and the raw upper bound, and then I've got the lower bound and the upper bound that I get from solving that quadratic programming problem. So the one that's kind of the convexified version. All right. So, and then here's the actual price they're paying per click. So this guy was paying 32 cents per click. The upper bound on his value per click was about 33 cents, and his lower bound was about 32 cents, and was paying 22 cents. So the first thing you want to see is, does the upper bound and the lower bound kind of align reasonably well with how much he's actually paying? I mean, obviously you want him to do more. He's only doing this because he's making some profit. But what you can do is you can take the value per click and then go back and look at that conversion probability. So how likely is that to convert to a sale? So maybe the conversion rate is, let's say, 2%. So you can take this 32 cents, divide it by the 0.02, and I think I get $16, huh? So then it says the value per conversion should be worth about $16. So then you go look at what this guy's selling and say, well, does the value per sale of $16 make sense? And yeah, it always makes sense. As it turns out, it's always kind of a pretty reasonable amount. And so if you look at that cost per acquisition, you can go look at mail order catalogs, you can look at direct marketing, you can look at lots of other stuff and see what typical cost per acquisition look like. And these are all consistent with that. And it kind of has to be, right? Because if it wasn't consistent with typical cost per acquisition, then why are they bothering to advertise here? I mean, you would expect to see that in equilibrium, the cost per acquisition across different media would tend to be equalized. And very least, they should be kind of roughly similar.
Just to
yeah.
make sure I've got that right.
Yeah.
What we're saying is the guy is paying, let's say, 22 cent price on bills. You've got to have a lower bound to the value, so it's about 10 cents.
Yeah.
10 or 11 cents in the fitted model and.
Yeah. So for that guy.
The raw guys are it could be like 3 cents. Number 4, row 4.
Yeah, row 4. So there you've got a fairly wide bound between the lower bound and upper bound on the raw, 25 to 42. But the bounds on the fitted are pretty tight, around 33 cents, and the price is around 22 cents.
Yeah, number 8 is a real interesting one too.
Yeah, well, the raw lower bound, I mean, the trouble is, you don't get a lower bound for the last guy, and you don't get an upper bound for the first guy, because there's nobody below him. So the 5 cents in this particular case, that was the minimum, that was the reserve price. So you know it's at least the reserve price, because otherwise you wouldn't be advertising. And the upper bound, well, I don't know why it's so large, but that's the way it worked out.
Okay, so when you think about 6, 7, 8 is the positions?
The 8 different positions on the right-hand side of the page.
How come number 6 is 38 cents and 5 is 22?
Oh, well, remember, this is the cost per click, and they're ranked by the click times the ad quality or the predicted click-through rate. Yeah.
So there's no sense here that maybe I want to pay a real high amount to have repeat buyers of a product, and once they hit my site once, I know they'll come back again without having done this. Is that going to the problem?
So
differences in the pricing based upon products?
Yes. So in fact, in this case, in the price per click would presumably reflect the lifetime value of a customer. So suppose you're selling a product that has a lot of repeat buyers, like wine, or the one that shows up actually is vitamin pills and diet pills and things where you're going to be taking them repeatedly. Well, they are willing to pay quite a bit for a customer because the hope is that once they try their particular product, they'll keep coming back and back for more. So on the other hand, you have some products where there's just they maybe only visit once. So nice one is debt consolidation. That's one I had before. So you hope that you are going broke every month, and in that case you might just get one visitor. But on the other hand, debt consolidation, they make a lot of money by consolidating these debts. So you want to look in reality. Then there's another component besides this lifetime value of customers. There's also the issue of brand value, because when I see this ad for whatever product is, it may be that the brand makes an impression on me as well. So it's not just the expected profit from this visit. It would be the profit from this ad impression and future visits that we might get. And indeed, offline purchases. Okay, so bounds on values. Okay, so that's pretty much the conclusion. Oh, well, I got one more thing to say on this. So this is pretty much a conclusion. Nash equilibrium seems to describe the data pretty well. The values are reasonable. Let's see, I guess I didn't really talk about the other 2 points, so I'm not going to emphasize them here. I do want to say a word before I leave this section of the talk. I want to say a word about the how you might have a different auction. So remember, the Google auction doesn't result in truthful bidding, but you could get an auction, a VCG or Victory Clark Groves auction, that would result in truthful bidding. So remember, in a VCG model, you say, if we charge everybody the marginal cost that they impose on the other people, then it's going to be in their interest to reveal the truth. So we could go out and ask, what happens in this context? Think of a model where each advertiser reports the value per click. We assign the advertisers to positions to maximize the total value of the page. And the payment of advertiser I is going to be the value accruing to the other advertisers if I is present, minus the value accruing to the other advertisers if I is absent. Well, think about it. If the guy in position 3 isn't there, the guy in position 4 moves up 1. And the guy in position 5 moves up 1 position. And the guy in position 6 moves up 1 position. So if you pull an advertiser out of the auction, everybody beneath him shifts up by 1. And so what's the total value that accrues to all those guys? Well, they were in position J, and now they're in position J minus 1. And we look at everybody who's in a position lower than Mr. I, and we sum that all up, and that's going to be the payment by Mr. I. Now, it turns out that if you just look at that expression and you go back a few slides, that's the same expression I had in the equilibrium of the Google auction. So it turns out that the dominant strategy equilibrium for the VCG auction is the same as the lower bound on the Nash equilibrium in the Google auction, the general second price auction. Yeah, so that's a very nice result. Unfortunately, it's a generalization of something that, it's a simplification, not a generalization of something that's already known. It turns out there's a series of papers by David Gale and his co-authors that show that's true for a generalized assignment problem. So if you take a generalized assignment problem where there's just a value of advertiser I being in slot J, so call that Bij, doesn't necessarily have to be multiplicative the way I had it here, then indeed the Vickrey-Clark-Groves mechanism gives you the same outcome as the lower bound of the market equilibrium. So this is what's nice about this case is, first of all, it's kind of a nice motivation that this is a special case of that general assignment problem, but you can calculate the solution explicitly. Okay? But it turns out to be true in generality. Okay, so that's part of the presentation. How long am I supposed to talk? 20 more minutes. Okay, I won't talk that many more. But I'll. All right. I'm going to do a very quick run through this because you've seen most of it, but I just want to introduce two sort of new ideas. So, yes, I wrote it on Christmas Day, and everybody remarks on that, but the reason is the AEA meetings, American Economic Association meetings, were right after Christmas, and I was scurrying to get this done, so I was one of those busy elves writing my report.
No Command L, you can use it a little quicker.
Oh, yeah, Command L, all right. Let's see here. All right, so there's only one new idea, there we go, in this. But I'm going to zip through the first part because it's kind of a useful reminder of where we've gotten. Here's the picture of the Google web page. There's the top ads. There's the right-hand side ads. Why do we have an auction? So I explained this all before. You want to price all these keywords. This is pretty much the same notation as I had earlier. These are the same rules that I had. And this is Joe's, Jets, and Mo's models that I was talking about earlier. Why do you want to rank ads by bids per click? Why? Because you're really selling off impressions. So this is just a quick review to see if you're paying attention. And even though it's really nice to be able to bid by impression, problem is you have to estimate the clicks per impression. But by the way, it's worth thinking about that for a minute because somebody has to estimate how many clicks you're getting per impression or how many sales you get per impression in order to figure out how much it's worth. So either the advertiser does that or the search engine does it. And the search engine is in a somewhat better position to do it because they have all these billions of observations. So it's kind of economizing on the total cost of producing this information to have the search engine do it. All right. So this is the same information I had earlier. They're competing for the incremental clicks. Auction's efficient. This is the Nash condition. This is the recursion. So I write it for the guy in position 1, the guy in position 2, the guy in position 3. I sum it up and I get the expression for total revenue. I've got the revenue bounds, the lower bound and the upper bound, just like I had before. And, oh yeah, well this is just sort of a cute observation that we should make before I go on is, think about an auction where all the positions were worth the same amount. Okay, so instead of being in a column, maybe they're in a row or something. So then X1 would equal X2, and X2 would equal X3. You'd get the same number of clicks no matter where you are. And so then what do you get? You just get an nth price auction. So it's just like selling n different slots, and you sell at the n plus first highest price. All right? Not very deep. So this is also just a generalization of the nth price auction. And as I mentioned before, it's a specialization of the Demange-Gale-Sotomayor two-sided matching model. All right. Here's the VCG auction. Truthful bidding is a dominant strategy. And here I'm doing the same arithmetic I did before. How much extra you would make if bidder 1 went away. And you get the same bound as you had before. So it's just a quick run through what you've already seen. All right. But Now we'll start the new stuff. But the problem is, you need to know those position-specific effects. You need to know how many clicks you get in position 1 and how many clicks you get in position 2 and so on. And that can be kind of difficult to figure out, potentially. Is there another way to get the dominant strategy equilibrium to run that VCG auction without having to know these position effects? So there's 3 different interpretations you might have. You could have how many clicks the ad in positions S got. So that's a random variable. It's going to differ on different days and different times you repeat the experiment. You can see the actual number of clicks it got on any given day. So that's the realization of that random variable. And you can look at the expected number of clicks that you would get. So before, when I was talking about the click-through rate, the right interpretation is how many clicks you expected to get in a particular position.
That's when you said people refer up by experimentation.
Yes. Yeah. Figure out the average number of clicks that you get if your ad is in position 2. Raise your bid a little bit, see how many extra clicks go up to position 1, see how many extra clicks you get there. So you can figure that out by experimentation and repetition. But VCG is charging based on the expected cost that an advertiser is imposing on the other people, or what the difference would be on average if you were there versus not being there. But what if we did it based on actual clicks? Okay, so then what would happen? So here's how we're going to do it now. We're going to say when a click occurs on an ad in slot S, charge the advertiser S the bid of the advertiser below him, just like we do in the second price auction, and credit each advertiser above slot S by BS minus BS plus 1. So we're charging the guys below him and we're crediting the guys above him. And then assume that the same clicks would have gone to the same slot even if some of the advertisers were absent. Turns out you get the same expected payoff as you get with VCG. And here's a little picture. So here's position 1, 2, and 3. You could have a click that occurs in position 1, a click that occurs in position 2, or a click that occurs in position 3. And now let's look at the impact on the other's value. If advertiser 1 is present, and there's a click in position 1, it doesn't have any impact on the other's value. And if advertiser 1 is absent, then the guy that's in position 2 would end up being in that position 1, and he would have gotten a click. So if advertiser 1 were absent, then the impact on the other's values would be V2. So in that case, the charge that we want to make to advertiser 1 is the cost he imposed on the other guy, namely impose the cost on the guy below him, because if he wasn't there, the guy below him would have been in the same position. If you get a click on advertiser in position 2, well, if advertiser 1 is present, then the guy that's currently in position 2 would get that value. But if advertiser 1 were absent, everybody would shift up 1, and the guy who was in position 3 would have gotten that click. So there's what happened to the other guys. Difference between what would happen if 1 were present and 1 were absent. And finally down here, I'll get to the question in a second, if there was a click on position 1, well then if advertiser 1 is present, the guy in position 3 gets it. If advertiser 1 is absent, everybody shifts it up, the guy in position 4 would get it. And that's the charge that's imposed on advertiser 1. So now, if you look, if there's X1 clicks of type 1, X2 clicks, X3 clicks, X3 clicks in the third position, the total payment that 1 is making is given by this expression, just adding up that bottom row, multiplied times the number of clicks, and that's just a rearrangement of this expression, which is exactly what we had before. So the expected value of doing it this way is exactly the expectation we had previously. Yes?
So here you have the assumption that in a sense it doesn't make a difference who's above me, just my position.
Right.
Okay, now come back to the Joe Jetson Bose model.
Yes.
So if I'm a model maker,
Yep.
and the 3 guys above me are all model makers,
Yep.
that's going to make a big difference as compared to the 3 guys above
Right.
me being Joe
Right.
Jetson.
So what you have to do in that case is just, instead of putting 1 here, put E1, E2, and E3. That's the expected number of clicks you would get. And then the algebra just works out exactly the same way. So it generalizes to that case. All right. Now, so you get the same expected revenue as VCG. It just adds up the clicks using a different grouping. You don't need to know the position effects. So that's kind of cute. I didn't really realize this till a couple years ago. But you don't need to know that. You can kind of estimate the number of clicks and do the incentives at the same time. All right, so then the second thing I want to say, and this is the last part of the talk, is let's get away from all this game theory stuff and all this calculation. Let's just think about it from the viewpoint of the advertiser. And this was much along the lines of what you were saying earlier. From the advertiser's point of view, all he knows is if he increases his bid, he gets more clicks. And if he decreases his bid, he gets less clicks. So somehow the reduced form of all this should be that expression that says, what's the relationship between the bids and the number of clicks, and what's the relationship between the cost and the number of clicks. So if I want to get 100 clicks, how much do I have to bid, and how much do I have to pay to get that? So think of those as just reduced form empirical relationships. The advertiser's behavior is to maximize value of click times number of clicks minus the cost of clicks, where that's something that's just been determined by experimentation. Well, we can solve that problem. Value equals marginal cost. Just a continuous version of what I had before. Once you know the number of clicks that maximizes profit, plug that into the bid function, and then figure out the bid that you need to bid to get that number of clicks. So it's a very sort of simple Econ 1 sort of calculation. And in fact, we can draw Econ 1 kind of pictures, because we can say, here's your marginal cost, here's your average cost, here's your value. We can read over here and see how many clicks you get. Once we know how many clicks that is, we can go up here to the bid function and figure out what the bid has to be to get those number of clicks. So as soon as the advertiser knows the relationship between the cost and the bids, you can figure this out. Now, one sort of nice thing would be, why don't we just tell them that? And indeed, there are some plans moving in a direction along that line to try to say, well, here's the relationship between the cost and clicks. Bid the point you want. So right now, advertisers have to figure this out by experimentation, but we can figure it out by looking behind the scenes. And indeed, it would be very useful to present that information. But what I really want to show you is on the next slide, which is saying, being able to use that reduced form expression in conjunction with an assumption that they're doing an adequate job of maximizing profit, and get an idea of the value of the search engine advertising. So let's just suppose that advertiser A could contemplate cutting its bid by some large amount. Suppose it cut its bid in half. And he's doing a good enough job of profit maximizing that if he cut his bid in half, he'd make a lower profit. Okay? So that's the expression that's given on that page. If he cut his bid in half, he'd get fewer clicks, and let's assume he would make lower profit. So that says his value has to be at least as big as this marginal cost. I mean, now it's not a little margin, it's kind of a big margin. You know, delta C over delta X. Multiply that times the number of clicks he's getting. Sum it up over all the different advertisers, and we get a bound on the total value in the market. The total value that's being created, which is on the left-hand side, is bounded by the expression on the right-hand side. And in fact, if you just divide both sides by total cost, here we get value over cost is bounded by a particularly simple expression. You can do the geometry of that. I know I'm running a little short of time, so I'll skip the geometry. And all we want to do is just estimate this. So we can go into the auction, and we can say for each person, if they cut their bid in half, they'd move down to a lower position, they get fewer clicks. We see how much I'd have to pay to be in that lower position, so we can calculate all those expressions that I had there. So you can run through the entire sample of auctions and get an estimate of the value-cost ratio. And it turns out that if you do that, start with an observed choice, cut the bid in half, determine the position from the auction rules, determine the price from the auction rules, forecast the clicks, that's the only problematic part, but we can use that model that said we've got an advertiser effect times a position effect. You could look at the observed clicks times the ratio of position effects. So as soon as you see what position he's in, you can figure out how many clicks you get, roughly. And you perform those operations, it turns out you find that the total value over cost is at least as big as 2, and it's less than 2.3. So you get a measure on how much value is being created in this market by basically using the value equals marginal cost to get an estimate of the value, and then by using the all this other stuff to get the value cost ratio. So the tightness of the bounds is going to depend on the curvature of that cost function. If the cost function were linear, then the bounds would just be, the upper and lower bound would be the same. If the cost function is highly convex, then you get the value cost range would be larger. But it's pretty tight. Turns out it's not too highly curved. You can estimate this by vertical, by country, by position, by all these different ways, and kind of figure out how much value is being created in all these different markets. So the conclusion is a very nice example, I think, of a two-sided matching theory. You can do VCG even easier than one might have thought, and I would argue at least that you're generating substantial economic surplus by putting this market in place. You're creating a lot of value. And that's probably a good place to end. So. Yes?
I think your first bullet point is where it says that you've made substantial progress in moving us forward on two-sided matching problems. Would you care to comment that this is the way boy will meet girl in 2020 or 2030?
So I will cite the literature on that. Ali Hurtaksu is at the University of Chicago has written a very nice paper called "What Makes You Click?" And it's a study of online two-sided matching problems. And he derives several general insights. There are a lot more blondes in online dating markets than there are in the rest of life. And having a shaved head is far more attractive than having a bald head, and many things of this sort. Yes, I know some people don't think so, but this is what the revealed preferences indicated. So there's a lot of nice work in this area. So anyway, questions? More questions?
Something in general about the aggregation of the data.
Yeah.
And whether or not you have looked at the number of clicks in recent years, and recent times, call it bid prices, and whether or not you see something in the tea leaves about recovery of the industrial sector of the economy.
So the question is, how well does this, looking at this data about what people are clicking on and how they're behaving, does that say anything about the level of economic activity? And the answer is sure. I mean, all commerce kind of moves together in the sense that people can think about buying a book online or buying it offline, or buying a toy online or buying it offline. So there's obviously some correlation there. We do have a very nice system called Google Trends, where you can go download a measure of the query activity on whatever queries you want. So I've been looking at these for various economic variables like automobile sales, tourist destinations, housing sales, that kind of stuff. And indeed, it is quite correlated with contemporaneous economic activity. Now the question is, does that allow you to predict the future? Well, it does in a limited sense because, of course, economic statistics are released with a lag. So halfway through March, you can kind of figure out what the real estate queries are looking like. And then in the middle of April, when you see the data released by the various agencies, you can kind of predict what that will be. So it isn't necessarily something about predicting the recovery out in the future, but predicting the near-term future seems to work pretty well. Yes?
So I was thinking about models of the behavior of the buyer.
Yep.
See, one story would be that there are some guys who click just the top one, and buy the top one. And some guys search 2,
Right.
some guys search 3. Presumably, if that were the behavior, the guy with the top slot would overcharge. And
Overcharge.
A higher price because there's no competitor. Many of his users have not looked at a second.
Oh, I see. Yeah.
And
So it turns out this is a little bit like the diamond search model, if you think about it. There's a cost to search. And there is a nice model by A.T. and Ellison, which is looking at basically there's a cost to clicking in an ad, and different people have different costs, and they'll click on different numbers of ads because of that. And so they work out the same sort of framework for, so in this paper, with that more detailed model of search behavior. So it's a very nice paper.
I wonder why I always go to the second one. I avoid the
Well,
first.
no, that's good. Yeah.
Thanks for explaining my behavior.
There you are.
So it's like you know, the best selling wine's always the second lowest price wine. So yeah.
Can you sell exclusive ads?
Exclusive ads.
So one ad on the page.
No, we don't do that. We have a situation where, I mean, we talk about it sometimes. I mean, it might be that you're saying, I'm willing to bid so much to be the only ad on the page that I can make it more profitable to do that. It turns out there aren't really huge externalities between the ads. There's some, of course. Because the model I had here was every ad kind of operating on its own, and the number of clicks that one ad gets is kind of independent of what the other ads get. So that's obviously an idealization, but it's not terrible. And I think that philosophically the idea is you'd like to give the users a lot of choice. So, because remember, you're trying to make sure the user has a good experience as well, and just showing the user one ad would not necessarily be the best experience. Because if we knew exactly what it was the user wanted, that might be okay, but different users want different things. So maybe one guy wants to buy the jet and the other guy wants to buy the model. So it's a good idea to show both ads. Yeah. Well, there is so it turns out that on TV they have all sorts of rules like this, where a set of ads in a given time segment is called a pod, and a typical rule is that there'll be only one auto ad per pod. But it's not necessarily because they're willing to bid so much for exclusivity. It's really more the fact that people get those auto ads all confused. Because what do? You see some automobile driving down the road. They all look the same. So the advertisers don't want people to get confused among the ads, so they try to make sure they're separated in time. So it's like beer commercials. You see somebody drinking a beer. So.
Could you effectively get exclusive rights by having, however many spots are?
Yeah, well, it's true. It's true. There's a limited number of slots. So in Google, for example, in the U.S., most parts of the world, it's 11 slots. There's up to 3 top ads, and there's up to 8 right-hand side ads.
Can you bid for multiple spots
No, there's only one ad from a given advertiser per page. Right. No, there's an exclusivity there in the sense that you don't want the same ad to appear multiple times. That would be a bad user experience too. Because remember, I'll get this in a second. The real issue is you want users to have a good experience from clicking on these ads. Otherwise, they'll stop clicking on them and stop looking at them. Yeah.
My experience is sock puppetry.
What?
There's ads that the teaser lines are different. Yeah. You click, you find out they're going to the same destination.
Yeah. So it turns out there's 2 things. That's called landing page quality. Now, there is a little exception to this rule, which is called affiliates. So Amazon, for example, has all these affiliates who are also selling things on Amazon. And so it may be that sometimes there'll be two ads for them. Ads for Amazon and ads for an affiliate. Or it may be when you look at cars, you have the car manufacturer, Chevrolet, could have an ad, and then all the Chevrolet dealers could have an ad. So it's kind of whether it's a different business unit. The question about whether they're going to the same landing page, I would say normally not, but I imagine there would be exceptions of the sort you described. Because, again, it's not such a good experience for the user because they've paid the cost of clicking this ad and they see what they've already seen before. That's bad from the user's point of view. Yeah.
I was thinking of the inequalities we had value surplus to cost kind of ratio between 2 and 2.3. And embedded, at least I think that I followed what was going on, but embedded in what that was these experiences of the users that are generating the current cost and bid functions out there, which they have to try to experiment around to figure out. And you were raising the point, well, why not just tell them?
Right.
And so would you sort of conjecture that if you change the auctioning environment to reduce those kinds of transaction costs, so it's like they got this continuous thing that's there, and maybe a little program that works it out for them.
Right.
You
Yeah, so what you do is you'd be taking some noise out of the system. So my view from looking at this data is that the advertisers who are making a lot of money, I mean, they're getting a lot of clicks, they're really quite sophisticated, and they've figured this out about how many clicks they'll get with different positions and different keywords and all this stuff, because there's just so much money at stake that it's very much in their interest to do that. On the other hand, the smaller advertisers might not have that much sophistication or resources at their disposal, so being able to give them better guidance about what these relationships between bids and clicks, between costs and clicks, that would be really quite valuable. And so, as I say, there are moves afoot to try to provide more information to advertisers so they can bid more intelligently. I don't think that's going to make big changes in the aggregate, but I do think it will eliminate noise or reduce the noise in the system. Okay.
Thank you very much.
Thank you.